Hi guys, and welcome to the Chapter 6 lecture, which is all about intermolecular forces. And if I had to pick a favorite chapter in the book, this one might be it. I think intermolecular forces is probably the most important topic to sort of understand in terms of chemistry and in terms of how chemistry works. It's up there with chirality and enantiomers in terms of how cool I think it is, in terms of how much it explains about how things work. So we're going to be talking about what intermolecular forces are and how intermolecular forces determine a number of chemistry properties, including solubility, melting point and boiling point, and actually, I think those are the two big things that we focus on: solubility and melting point and boiling point. Okay, so this is the chapter outline. So intermolecular forces are different than intramolecular forces. Okay, so intra means within, and inter means between. So intramolecular forces are forces that are within a molecule, are bonds that you have between atoms within a molecule. So for example, water, H2O, those are two hydrogens that are covalently bonded to that oxygen. Covalent bonds and ionic bonds are intramolecular forces. They're forces between atoms within a molecule. Okay? So if you look at my little stick figures here, they're sort of supposed to be analogous to the structure of a molecule. It looks kind of like a skeleton structure. So maybe these 2 points here are carbons, and the little green dots, the hands and the feet, and the head could be, hydrogens and oxygens or something like that. So these arms, the sticks, the arms here represent intramolecular forces, like covalent bonds, okay? And you can think of it the same way with your body. You have, your arms and your legs and all these different, parts. So your arms are bonded, keep your hand bonded to your shoulder, okay? And they are within, maybe that's taking it too far. So those are intramolecular forces. Intermolecular forces are forces or attractions between two different molecules. So if you have two people holding hands, okay, they are attracted to each other and they're holding hands, so there's a connection, attractive force between these two people. Same thing with molecules. You can have two molecules that are essentially holding hands. They're attracted to each other and they sort of stick together, but it's a much weaker kind of a linkage than, say, the bonds within the molecule. So my other analogy here is that it's intermolecular forces and intramolecular forces. It's like a game of Red Rover, if you ever played Red Rover. Red Rover, send whoever right over. So people stand in a line and they hold hands, and then someone from the other side comes running through and tries to break that linkage between your hands, okay? And if they run hard enough, they can break your hands apart. You let go, okay? Now, it's very uncommon for them to run through and actually break someone's arm, right? So the linkage between your hands is weaker than the linkage of the bone in your arm, okay? So the intramolecular forces that hold a molecule together are very, very strong. It's the intermolecular forces that are weaker and that get broken, can be broken more easily, okay? But still, intermolecular forces are significant. They do hold molecules together. And essentially, intermolecular forces are attractive forces between molecules that have a partial charge, okay? So an example here is I have two polar molecules. Don't forget about polarity. We talked about it in Chapter 3. If you need to go back and review it, do that. Okay, but a polar molecule is one where there's an electron hog, so either oxygen, nitrogen, fluorine, or chlorine, bonded to some other non-metal, and so that oxygen that electronegative hogs the electron, so you get a partially negative end and a partially positive end of the molecule. So because they have partial charges, those partial charges can be attracted to each other. So the partially negative end of molecule A can be attracted to the partially positive end of molecule B, and they essentially come close together and hold hands. So there are different types of London forces, of intermolecular forces. There's 3 different types of intermolecular forces that we'll talk about: London forces, dipole-dipole attractions, and hydrogen bonding. And this is a little diagram from your book that's very helpful because it also sort of illustrates that which forces are stronger and which are weaker. So London forces are the weakest, dipole-dipole attractions are stronger, and hydrogen bonding forces are the strongest. And we'll talk about why that is when we go through each of these. But London forces occur in every single molecule. Again, I'll talk to you in a second about why that is, but if we're talking about can a molecule engage in London forces, London attractions, the answer is always going to be yes. Every molecule has London forces. Only some molecules have dipole-dipole attractions. Which molecules? Polar molecules. Only polar molecules have dipoles, so only polar molecules can have dipole-dipole attractions. And hydrogen bonding is even more sort of exclusive and only occurs in polar molecules that have a hydrogen bonded to one of these 3 electron hogs: nitrogen, oxygen, or fluorine. So I'll remind you of each of these as we go through them. So London forces. What are London forces? London forces are kind of interesting, a little bit abstract. Okay, so another term for London forces are induced dipole or dispersion forces. Okay, and the reason is induced dipole probably says it best what it is. So what happens is this is a diagram of an atom, right? The blue dot is the nucleus, and the larger blue circle is the electron cloud around the nucleus. So remember, we talked about electrons sort of orbiting in these different shells, but we said that really, in honesty, they sort of fly around in this cloud. Okay? So you have all these electrons flying around in this cloud, and they don't always fly around in sort of an even distribution. Sometimes, for like a split second here and there, you might have more electrons on one side of the cloud than you do on the other. So an atom, even an atom that is not normally, or a molecule that you wouldn't consider to be polar, can have a tiny little temporary dipole formation because of that dispersion of the electrons unequally in the molecule. So for a split second, you get this sort of scenario in an atom. The electrons are unevenly distributed in the cloud, and it gives the atom a slight dipole moment. Okay, slight, gives them little poles. So this atom is sitting next to this atom here, which has an even distribution of electrons. And what happens? Well, the positively charged end of this, sort of the partially positive charged end of this atom, induces a dipole in the second atom. It attracts electrons. So this positively charged end here attracts electrons from this other atom it's sitting next to and induces a similar shape, induces a change by attracting the electrons to this side of the atom. Okay? So this is happening all the time in all molecules all around us. The atoms, the electrons are shifting, and this happens for a split second, at different, times. I don't know how often it happens, but it happens, okay? So every single molecule has this happen. Even if the molecule is polar, the individual atoms in the molecules will be engaging in this kind of behavior. Even if it's nonpolar, even if it's just a bunch of carbons and hydrogens and it's totally a nonpolar atom, there's no dipoles on the molecule. Each of those carbons and hydrogens are atoms that look like this, I suppose, and can be converted to a situation like this. Okay? So who can experience London forces in terms of the molecular world? All nonpolar molecules and all polar molecules. So all molecules experience London forces because they occur from formation of these transient temporary dipoles in atoms. And they're pretty weak. They're pretty weak types of interactions because they're pretty subtle dipoles that form. But if you have a molecule that has only a few atoms in it, like, I don't know, ethane, okay, which is C2H6. So there's 8 atoms total, 2 carbons, 6 hydrogens, 8 atoms total in that molecule. The London forces between those in that molecule are going to be pretty small because it's a fairly small molecule. You take something like a fatty acid, which has like 26 carbons and I don't know how many hydrogens is that, like 30 hydrogens, something in that ballpark. Okay, the longer that nonpolar molecule is, the larger that molecule is, the more atoms it has engaging in these London forces. So the larger the molecule is, the more London forces you have, and the stronger. And so London forces can actually be quite significant in terms of larger molecules because they add up. They're additive. So London forces are actually how cling wrap works. So like saran wrap, when you like wrap something up and the saran wrap actually sticks to itself, it's kind of like staticky. That is actually because of London force attractions. So you have your it's basically long hydrocarbon chains in the plastic, and when you get it close together, it causes this disturbance of the electrons. So here it's showing you how the electrons suddenly get distributed all to the pink side of the molecule. So you get this partially positive charge on top here and a partially negative charge on the blue side down here. And so then then that's why it causes that attraction. So you get that stickiness, that attraction of the plastic to itself because of the way that the electrons are actually distributed in the molecules. It causes an electrostatic attraction. And that's shown here. So the negative side or the positive side of one is attracted to the negative side of the other. Okay, so that's London forces. London forces are temporary and transient dipole interactions. A dipole-dipole attraction occurs in molecules that have a permanent dipole, so that the molecule is polar and therefore always has this dipole, not because the electrons are shifting around spontaneously, but because the electrons are constantly attracted to an electron hog in the molecule. So here's a molecule of ether, actually, CH3OCH3, okay? It's in a bent structure like water. And the oxygen is an electron hog, so it's going to hog electrons and give the oxygen side of the molecule a partially negative charge. And the 2 methyl groups down here a slightly positive charge. And the molecule, it's a polar molecule. It's always going to look like this. It's always going to have these dipoles, a partially negative side and a partially positive side. So those dipoles then the molecules can sort of line up according to their dipoles so that the positive and negative ends are attracted to each other and are sort of connected. And these are pretty strong attractions because they're permanent dipoles and opposites attract. So if they're permanently positive and negative, they're permanently attracted to each other. So here's a question for you. Can nonpolar molecules have dipole-dipole attractions? No, they cannot because why? They don't have dipoles. So if a molecule doesn't have a dipole, in other words, if a molecule is not polar, then it cannot have dipole-dipole attractions. Which is stronger, London or dipole-dipole forces? Dipole-dipole forces are stronger because they are permanent, whereas London forces are sort of similar to this in terms of their functionality, but they're temporary. They only occur sort of sporadically. And so they are not as strong. So dipole-dipole forces are stronger. The third type of intermolecular force we're going to talk about is hydrogen bonding. And technically, hydrogen bonding is a form of a dipole-dipole attraction or a dipole-dipole force. But it's a very, very strong, it's the strongest type of dipole-dipole attraction. Okay, so the hydrogen bonding is sort of defined by the fact that, okay, you have to have a hydrogen bond acceptor and a hydrogen bond donor. Okay, so a hydrogen bond acceptor is either a nitrogen, oxygen, or fluorine that has a non-bonding pair. Okay, so if a molecule has a nitrogen, oxygen, or fluorine with a lone pair on it, and pretty much all of these molecules always have a lone pair, then it can accept a hydrogen bond. You also have to have a hydrogen bond donor involved, and a hydrogen bond donor is any hydrogen that's bonded to a nitrogen, oxygen, or fluorine. Okay, so any of these hydrogens here can engage in hydrogen bonding because they are bonded to either a nitrogen, an oxygen, or a fluorine. So that's the key when you're looking for hydrogen bonding. If you want to know if hydrogen bonding is a possibility for a molecule, you have to ask, is there a hydrogen that's bound to a nitrogen, an oxygen, or a fluorine? Okay? Then that nitrogen, oxygen, and fluorine, each of those can act as hydrogen bond acceptors. So all of these molecules these three on the right here are hydrogen bond donors, and technically they also can be hydrogen bond acceptors. So the donor being the hydrogen, the acceptor being the nitrogen, oxygen, or fluorine. The other thing is you can have molecules that, although they don't have any hydrogens that participate in hydrogen bonding, they can be the acceptor of the hydrogen bond. Okay, so let's look at some examples here and sort of explain that a little bit more. So where does this come from, the whole acceptor and donor? It has to do with poles again, okay? It's still dipole-dipole that we're talking about here. So let's look at water. Water looks like this. This is the Lewis structure for water. There's an oxygen that's bound to two hydrogens, but also it has two lone pairs, okay? And those two lone pairs, the oxygen up here is partially negatively charged, okay, because it's an electron hog. It has a very high electronegativity. And the hydrogens down here are partially positively charged, and their electrons are being stolen up here, hogged by this oxygen. So when you have multiple water molecules together, you have the partially negatively charged oxygens attracted to the partially positive charged hydrogens. So as you can see here, there's hydrogen bonds are always represented by a little dotted line between molecules, okay? So you have this little dotted line connecting hydrogen of one to the oxygen of another, the oxygen of one to the hydrogens of the other, okay? So one oxygen has two lone pairs, so each of those lone pairs can actually engage in hydrogen, can attract the hydrogen of another molecule. So one water molecule basically has 4 sites for hydrogen bonding. 2 acceptor sites, these 2 negative sites are sites of hydrogen bond, they can be hydrogen bond acceptors because they're partially negatively charged. And these two positively charged hydrogens can be hydrogen bond donors. They sort of, donate the hydrogen there. So here's another picture sort of labeling that. So you have your water molecule, your O and your two H's. The D's mean donor, so these hydrogens act as donors, and each of the lone pairs on the oxygen act as acceptors of hydrogen bonds. Okay? So hydrogen bonds can exist between two of the same molecule. So like if you have a whole bunch of water, the water molecules can all hydrogen bond with each other. But also, if you mix two different polar molecules together and both of them are either a hydrogen bond donor or a hydrogen bond acceptor, you have at least a hydrogen bond donor and a hydrogen bond acceptor, you can get hydrogen bonding between different types of molecules, okay? So, for example, here's acetone in water and ethanol in water, okay? Both of these scenarios, you have water hydrogen bonding with another molecule. So in the case of acetone, acetone is a hydrogen bond acceptor, but it is not a hydrogen bond donor because it has an oxygen. So when you're looking at for hydrogen bonding, the first thing you want to look for is nitrogen, oxygen, or fluorine. Does it have one of those three? Because if it doesn't, it's not going to be able to hydrogen bond. So acetone has an oxygen, okay? Secondly, we want to know, does it have is that oxygen, so that oxygen is going to act as a hydrogen bond acceptor. The question is, does it have any hydrogens that can act as hydrogen bond donors? And there are no hydrogens in this molecule that are attached to an oxygen, nitrogen, or fluorine. So therefore, it only has a hydrogen bond acceptor. This oxygen is a hydrogen bond acceptor, but there's no hydrogen bond donors. So acetone can engage in hydrogen bonding if there's another molecule around that has hydrogen bond donors, like water. Water has hydrogens that are attached to oxygen. So the hydrogens, the partially positively charged hydrogens in water, are attracted to the partially negative lone pairs on the oxygen molecule in acetone. Ethanol is another molecule that can engage in hydrogen bonding with water in two ways, because ethanol has a hydrogen bond acceptor. It's got an oxygen with lone pairs, but it also has a hydrogen bond donor because it has a hydrogen that's bonded to that oxygen. So it can engage in hydrogen bonding with water through its acceptor. The oxygen can bond to the hydrogen of water, or the hydrogen of the ethanol of the alcohol group can bond with the oxygen of water. Okay, so there's different ways to engage in hydrogen bonding. And lastly, you can also get hydrogen bonding within a molecule. So if you have a very large molecule, it can actually sort of fold up on itself, and different atoms within the molecule can engage in hydrogen bonding. And you'll see this big time when we talk about proteins and protein structure. Hydrogen bonding is very important there. So here's an example of a molecule where this red dotted line here is showing you hydrogen bonding. So the molecule itself is a straight chain, CH3O, CH2, CH2, OH. Okay? But the OH group here, that hydrogen is a hydrogen bond donor because it's a hydrogen attached to an oxygen, nitrogen, or fluorine, in this case an oxygen. So it's a donor, and the other oxygen is acting as the hydrogen bond acceptor. So they are engaging in hydrogen bonding together. So let's work some practice problems here. And we want to know, can the following molecules hydrogen bond to water? If so, how many hydrogen bonds can each make? And we're going to draw them. Okay? So first thing, I want to draw these molecules out a little bit bigger so we can see them a little bit better. Well, no, I don't. I just want to draw out okay, so first of all, we're being asked about hydrogen bonding. So the first thing we want to look for is, does this molecule have oxygen, nitrogen, or fluorine? Those are the electron hogs that we're looking for to determine whether there's any chance that there's going to be hydrogen bonding in this molecule. And yes, there is a there's an oxygen molecule. Oxygen, and I'm going to draw the hydrogen out here because I want to draw a little more detail. I want to draw the lone pairs here on our oxygen. Okay? So we want to know, can the following molecules hydrogen bond to water? So yes, this molecule can hydrogen bond because there's an oxygen. Is it a hydrogen bond donor, a hydrogen bond acceptor, or both? It would be both. It has the hydrogen that's attached to an oxygen, so that would be this hydrogen would be a hydrogen bond donor, and the oxygen with two lone pairs can be a hydrogen bond acceptor. So this one can be both a hydrogen bond donor and a hydrogen bond acceptor with water. So let's draw in, I don't know how to change the color of my line. Let's try this. Trying to make it like the picture, okay? So our hydrogen bonds will make little dotted lines. Oh, now how do I go back to black? Okay, so now this hydrogen is going to bond with water. It's going to bond with which molecule and which atom in water? The oxygen. It's going to be this partially positive hydrogen is going to be attracted to the partially negative oxygen in a water molecule. So here's my water molecule. OH and H. Okay. And then this oxygen how is it going to bind with water? It's going to be attracted to one of the hydrogens in the water molecule. Okay? Ta-da! So this molecule can bond with water hydrogen bond with water in two ways. The hydrogen can interact with the oxygen in water, and the oxygen in this molecule can interact with the hydrogen in water. Okay? How about this second molecule here? CH3CH2Cl. Can it hydrogen bond to water? What's the first thing we need to do? We're looking for what? Oxygen, nitrogen, or fluorine. Does the molecule have oxygen, nitrogen, or fluorine? No, it doesn't. So the answer is it will not hydrogen bond with water. This molecule cannot engage in hydrogen bonding. There's no oxygen, nitrogen, or fluorine. Easy enough. How about this one? Is there an oxygen, nitrogen, or fluorine? Yes, there is. Let's draw this molecule out. We have to draw the Lewis structure of this molecule. And it's not exactly straightforward. If you need practice drawing Lewis structures, go back to Chapter 3 in review. So carbon has 4 arms, right? It looks like this. I mean, this is the structure. But we have to figure out how this carbon and nitrogen are bound together. Carbon has 4 arms total. Nitrogen has 3 arms total. And there's 3 arms left for this carbon. So the way that they're going to be bonded is actually those 3 arms remaining for the carbon, and the 3 arms the nitrogen needs, they'll all be holding hands together, okay? And then the nitrogen's going to have a lone pair still out here because nitrogen has 5 total electrons, which give it 3 bonding arms and 2 as a lone pair, okay? So this is our molecule, and we want to know, does it hydrogen bond with water? And we say yes, because there's a nitrogen, or oxygen, nitrogen, or fluorine. Yes, there's a nitrogen. So this nitrogen can bond with water how? Is it going to be is it is it a hydrogen bond donor, a hydrogen bond acceptor, or both? It's a hydrogen bond acceptor. It can't be a donor because there's no hydrogens that are bonded to that nitrogen. So it can only act as a hydrogen bond acceptor. So here's our water molecule. And we're going to draw in the hydrogen bond. So that nitrogen is going to be attracted to the oxygen or the hydrogen. The hydrogen. So the nitrogen is partially negative charged and the hydrogen is partially positive charged. So there's our hydrogen bond. Okay? Ta-da! So practice those hydrogen bonding questions. Make sure if you're looking for a hydrogen bond, the first thing to ask is always, is there a nitrogen, oxygen, or fluorine? Okay? If there is, then yes, you can hydrogen bond with water. The next question is there a hydrogen bond donor or a hydrogen bond acceptor? Identifying those. Okay? So I think we have a couple more problems. Excuse me. 12 here. Identify the strongest intermolecular force that could exist between each of the following pairs of molecules. So first of all, what are the intermolecular forces we've talked about? London forces, dipole-dipole interactions, and hydrogen bonding. Which one is the weakest? London forces. London forces are the weakest. Okay, so let's just go through and say what forces could exist between them, period. Okay, so these two molecules, if we mix them together in a jar, would they have London forces, London attractions? You better all have said yes, because everything has London attractions. Okay, so yes, no brainer, don't even have to think about it, doesn't matter what kind of molecule they are, yes, there will be London attractions. Alright, now let's look at the two and ask, are there going to be dipole-dipole attractions between them? In other words, do both of the molecules have dipoles? Are they both polar? How about this one, the first molecule, is it polar? Well, how do you know if it's polar? What are you looking for? You're looking for an electron hog. Oxygen, nitrogen, fluorine, or chlorine. Okay? Does it have one of those? Yes, it does. It has an oxygen, so this one is polar. All right. How about this one? Is it polar or nonpolar? Is there an oxygen, nitrogen, fluorine, or chlorine? No, this is nonpolar. It's all carbons and hydrogens, and all hydrocarbons are nonpolar. We talked about that in Chapter 4. So this one's nonpolar and this one's polar. So can they have dipole-dipole attractions? No, they cannot. All right? If they can't have dipole-dipole attractions, can they have hydrogen bonding? No, they can't, because hydrogen bonding is a type of dipole-dipole attraction. So the strongest force that could exist between these two, are London forces. It's the only force that can exist between them. All right, next one, part B. Do these two have London forces? Yes, they do. Everything has London forces. Can they engage in dipole-dipole attraction with each other? In other words, are they both polar? Well, let's see. This one has an oxygen, so yep, it's polar. And this one has an oxygen, so yep, it's polar. So they're both polar. They can both have dipole-dipole attractions. Fantastic. What about hydrogen bonding? Do we have a hydrogen bond acceptor and a hydrogen bond donor? Let's see. Well, they both have oxygens, which suggests they could engage in hydrogen bonding, okay, but we have both a hydrogen bond donor and a hydrogen bond acceptor, because you need both. This oxygen here, is it a donor or an acceptor? This one's going to be a hydrogen bond acceptor. There's no hydrogen to donate, okay? There's no hydrogen bound to it. How about this oxygen? Is it a hydrogen bond donor or a hydrogen bond acceptor? All right. For those of you, just in case you're confused, I'm going to draw out this part of the molecule. These CH2, the H2 there is bonded to the carbon. The oxygen is here with its two lone pairs. And then another CH2 here. Okay, so is this oxygen a donor, a hydrogen bond donor, or a hydrogen bond acceptor? It's going to be a hydrogen bond acceptor. It also does not have a hydrogen bound to it. So if you have two hydrogen bond acceptors, can you have hydrogen bonding? No, you need an acceptor and a donor. So these will not be able to do hydrogen bonding with each other. These two molecules cannot hydrogen bond with each other. But they're both polar, so they can have dipole-dipole attractions. So that would be the strongest attraction between them. So technically, they have both London forces and dipole-dipole attractions, but the question is, which is the strongest force holding them together? So I'm going to write dip-dip for dipole-dipole. Okay? And now this last one here. Again, let's go through all three. London forces, check. Everything has London forces. Do they have dipole-dipole attractions to each other? In other words, are they both polar? We've got an oxygen here, so this one is polar. Check. And we have an oxygen in this molecule, so this one's polar as well. Check. So we do have dipole-dipole attractions. Now the next question is, do we have hydrogen bonding attractions between the two? Do we have a hydrogen bond donor and a hydrogen bond acceptor? Is this oxygen a donor or an acceptor? It is an acceptor. Are there any hydrogens in the molecule that are donors? No, because these hydrogens, the only hydrogens in the molecule, are bound to carbon. We don't care about that. We're looking for hydrogens that are bound to an oxygen, nitrogen, or fluorine, and there aren't any. So there's only a hydrogen bond acceptor in this molecule. How about this one? If I draw it out here. We have an oxygen. We have 4 hydrogens. So we want to know, so that oxygen we know can act as a hydrogen bond acceptor. Okay, so I'll go ahead and label that. Are there any hydrogens that can act as hydrogen bond donors? In other words, are there any hydrogens bonded to a nitrogen, oxygen, or fluorine? Yes. Ding, ding, ding. All right, this hydrogen here can act as a donor. This is a hydrogen bond donor. So this guy has a hydrogen bond donor, and this guy has a hydrogen bond acceptor. So yeah, they're compatible in terms of hydrogen bonding. So the last one has all three. It has London forces, it has dipole-dipole forces, and it has hydrogen bonding, or I should have just written H bonding. Okay? And there's several problems like that in the homework, so practice those. The fourth type of intermolecular force, sort of, is called ion-dipole attraction. So technically, it's not an intermolecular force because technically ions are not molecules. They're ions. Ions are ions. They're atoms with a charge. And molecules are atoms that are covalently bonded together and have no charge. Okay? So it's a little bit of a misnomer to call them intermolecular forces, but they kind of are. Because it's when a molecule is attracted to an ion. So an ion-dipole attraction is when you have an ion that's fully charged, that has a legitimate full charge, is attracted to a molecule that has a dipole that has a partial charge that's opposite. Okay? So for example, water, which has dipoles, a negative dipole at the oxygen and positive dipoles at the water, is attracted to, for instance, a sodium ion, which is positively charged, so it's attracted to the negatively charged oxygen. And chlorine, which is negatively charged, is going to be attracted to the partially positively charged hydrogen of water. Okay, so that's an ion-dipole attraction, and it forms if you have a polar molecule and you have ions. Okay. So all of these different intermolecular forces actually help determine a lot about the chemistry of molecules. So, and a lot of the physical properties of molecules. So this chapter talks a lot about solubility. This is where we talk about solubility. So what is solubility? Solubility is the ability of molecules to mix together and sort of evenly distribute. The ability of one thing to dissolve in another. And the golden rule of solubility is like dissolves like. Now, what does that mean? It means that molecules that have similar polarity and therefore participate in the same types of intermolecular forces will dissolve each other. That's what like means, like polarities. So polar molecules dissolve other polar molecules. Non-polar molecules dissolve other non-molar molecules. You cannot mix something that's polar with something that's non-polar. Hence the canonical statement that oil and water do not mix. Oil, being a type of fat, a type of hydrocarbon, is non-polar, whereas water is a very polar molecule. So they don't mix because they don't have the same types of intermolecular forces. So here's my two examples. An oil and vinegar sort of dressing that you can see is separated out. The oil and vinegar. Oil and vinegar don't mix. Vinegar is polar. And here's a picture of an oil spill in the ocean. And you can see the oil sort of sitting on top of the water. It doesn't mix into the water. They're actually cleaning up, trying to clean up the spill here. Okay, so like dissolves like, polar and nonpolar do not mix. So let's first talk about solubility of nonpolar compounds. Okay, so a nonpolar compound that's biologically relevant and that we've already discussed are fats, lipids, dietary fats. Okay, dietary fats are made up of triglycerides. So we talked about fatty acids, but we didn't really talk about how they form our dietary fats. So we talked about fatty acids, saturated fatty acids, unsaturated fatty acids, etc. But these fatty acids exist in our body in the form of triglycerides. So they mix with a molecule of glycerol. So you have glycerol, it's this molecule here, 3 fatty acids, and they combine to form what's called a triglyceride. Okay? And so this is the top picture here is showing you what all the molecules look like. Down here I have it written just in text. A glycerol plus 3 fatty acids is an oil or a triglyceride plus 3 water molecules is a product of the reaction. So, pop quiz from chapter 5, what type of reaction is this? Anyone remember? The hint is water over here, okay? This is a condensation reaction. Water is formed. 2 molecules are forming together to form one, and in the process you lose water. That's a condensation reaction, okay? So hopefully some of you guys recognize that. So something interesting about oils, if you've ever cooked in like a skillet or a pan and you get like all this greasy oily stuff on the bottom of the pan and you wash it and you have to scrub and you can't get that stuff off the bottom of the pan, that like sort of burned oil. The best way to clean that off actually is to use oil. Just pour a little oil in the pan and scrub with it, because oil will dissolve oil better than water dissolves oil. Soap can do a decent job, and we'll talk about how soap works in a second, but the best way to clean off a greasy pan is with oil. I like this picture because apparently the grease looks like Jesus, but I'm sure it's just photoshopped. Okay, so just a sort of conceptual review here. Why oil and water don't mix, okay? So what types of intermolecular forces are there between triglycerides? First of all, triglycerides, are they polar or nonpolar? They are nonpolar molecules, okay? even though triglycerides have some oxygens in here, they have very long chains of carbon and hydrogen that are nonpolar. So they're majorly there's a little bit of, polar points, but those polar points are very outweighed by how big the nonpolar region is. So triglycerides are nonpolar molecules. And, okay, so what types of intermolecular forces are there between triglycerides? Are there London forces? Check. Are there dipole-dipole forces? No, because they're nonpolar. Are there hydrogen bonds? No, because they're nonpolar. So the answer to this would be London forces. Okay, there's London forces between triglycerides. What type of intermolecular forces are between water molecules? Are there London forces? Yes. Are there dipole-dipole attractions? Yes. Are there hydrogen bonds? Yes. Water molecules have all three. They have very strong bonds, hydrogen bonds together. So which type of force is stronger? The hydrogen bonds in water or the London forces in triglycerides? The hydrogen bonds in water, okay? So picture this. Picture you have a whole bunch of water molecules. It's like a clique, okay, of like kids at high school. So these water molecules, they're all engaged in these really like tight hydrogen bonds, okay? And those are really strong attractions. Then you have all these triglycerides come in, you pour some oil into the water, and those triglycerides, they can't engage in hydrogen bonding. They can't break into that clique because they can't form those strong bonds. So they are forced to stick together with their weak little London forces and hang out that way because they can't break into that group of water molecules because they can't engage in hydrogen bonding. So they can't break the hydrogen bonds to make London, to have London forces. Okay, it's like you can't break up a strong friendship to have a weak friendship. Okay, so that's why they don't mix. They don't mix because they don't have the same type of intermolecular forces. The forces between the water molecules are very strong, much stronger than the ones between the triglycerides, so they're going to just stay that way. When it comes to polar compounds, though, they can mix with water because they can engage in dipole-dipole attractions and hydrogen bonding with water molecules. So a pretty good example of something that's soluble in water is sugar. We mix sugar in our tea, in our coffee, in our lots of things that have water in it, okay? And sugar, in this case sucrose, table sugar. We talked about sucrose being a disaccharide. It's one molecule of glucose and one molecule of fructose, okay? Bonded together. And there's a lot of hydrogens here. Glucose sugar molecules, are very polar. And these polar molecules can engage in different types of dipole-dipole bonding with water. So first of all, are there any hydrogen bonds that can sucrose engage in hydrogen bonding with water? Does it have any hydrogen bond acceptors or any hydrogen bond donors? And the answer is yes to both. It has, so for instance, this oxygen right here could be a hydrogen bond acceptor only, just like this oxygen right here is a hydrogen bond acceptor, okay, because it doesn't have any hydrogens bound to it, so it can only be an acceptor. But then all of these OH groups everywhere, all of these OHs can act as hydrogen bond donors to water. So there's a couple of water molecules that are drawn in here to show you some of the different ways that sucrose can hydrogen bond with water. But in fact, all of these oxygens, there's a lot of hydrogen bond donors and acceptors in a molecule of sucrose. So, sucrose, therefore, is very soluble in water because it can engage in hydrogen bonding with water. So it can break the hydrogen bonds between the water molecules and engage in its own hydrogen bonding with water. Those bonds are equally strong. So they mix together very well. Another type of compound that's very soluble in water are ionic compounds. because they can engage in ion-dipole bonding, which is actually very, very strong. Probably strong, is actually stronger than hydrogen bonding is. So when you mix an ionic compound in water, and what happens is, so this is a molecule of salt. Well, it's not really a molecule. There's no such thing as molecules of. There's no such thing as ionic molecules. There's ionic compounds because a molecule is like a discrete entity. Okay, so you have a water molecule is an oxygen bound to 2 hydrogens. There's sodium chloride is an ionic compound, but you don't really get like a sodium and a chloride molecule together. Like you don't have a sodium chloride molecule and have a whole bunch of sodium chloride molecules. You get a big giant crystal. So all these sodium and chloride ions are all attracted to each other and they form like a giant block. You don't get like discrete molecules. So anyway, you take a block of sodium chloride, you throw it in water, and the sodium ions and the chloride ions will break off and get surrounded by water molecules engaging in ion-dipole bonds. Okay, so the partially negative side of the water molecule is going to be attracted to and surround the positive sodium ion, and vice versa. The partially positive hydrogen side of water will surround and be attracted to chloride ions. Okay, so when we call this is hydration. When you take an ionic compound, you throw it in water, and it dissolves and the ions get surrounded by water molecules, we say that they are hydrated, that you have hydrated that salt. Okay. So soap has a unique chemistry that allows us to sort of make a bridge between polar and nonpolar compounds, and allows us to sort of dissolve nonpolar compounds into polar compounds. So essentially, think about taking a shower, taking a bath, okay? Let's say if you don't take a shower for a couple of days, what happens? Your hair gets all greasy, right? So you get in the shower and you just rinse it with water. Well, nothing's going to happen because water won't dissolve the grease in your hair. What do? You have to use shampoo. You use soap to help wash that grease out, to wash the grease out into the water. And soap has this ability to take something nonpolar or greasy and dissolve it in something polar like water. And how does it do that? Well, it's because soap has a very unique structure. Okay? Soaps are very much like fatty acids. In fact, they're salts of fatty acids. So we talked a little bit about fatty acid structure being what we called amphipathic. It has a hydrophilic head group. So in a fatty acid, this would be a carboxylic acid group. In the soap, it's a carboxylate. So the carboxylic acid is a COOH, but the carboxylate is just COO with a minus charge. Okay, so this is going to be even more polar. It has an actual charge, so it's going to be even more hydrophilic. It's going to be more attracted to polar things and water. And then it has a hydrophobic tail. So the tail is nonpolar and it's afraid of water. Okay, so when you have a molecule that has a hydrophilic region, a polar region, and a hydrophobic region, a nonpolar region, we call a molecule like this an amphipathic molecule, kind of like ambidextrous, someone who can use their right hand and their left hand. An amphipathic molecule is both polar and nonpolar. Okay, so how does this help dissolve oils? Well, it's very cool actually. So soap forms what are called micelles in water. It forms like a sphere. It's essentially a big sphere where all of the hydrophilic head groups are on the outside of the molecule, and all the hydrophobic tails are on the inside of the molecule. So this is the nonpolar inside of the sphere and the polar outside of the sphere. So what happens is, soap molecules, the nonpolar tail binds to dirt and attracts dirt or grease, nonpolar grease. And that grease gets trapped in the center here of the micelle and gets completely surrounded by these soap molecules that are polar on the outside. So you can see here the outside can engage in attractions with water molecules. So this whole thing can dissolve in water, and inside of it is where the dirt is trapped. So that's how soap helps to remove grease and wash it away in water, because it actually traps the grease inside these spheres of soap molecules. Okay, it's pretty cool. So let's do a sample problem here. So before we were talking about we compared molecules to see if they had the same, what kinds of intermolecular forces they could engage in. This problem is very similar, except it's asking the question in a different way. It's asking to predict whether the molecules are soluble or not soluble in each other. In other words, do they fit the rule, the golden rule of solubility, like dissolves like? And when we say like dissolves like, do they have the same intermolecular forces? So let's look. It says, if soluble, identify the attractive forces involved in the interaction. If not soluble, explain why. So H2O and hexane here, are they soluble or not soluble? Hopefully you said not soluble. Can you explain why? Hopefully you said because water is polar and hexane is not polar. Remember, like dissolves like, we're talking about polarity. Are they both polar or not polar? And something polar is not going to be soluble with something not polar. So in this case, we've got water is polar, hexane is not polar. Okay, so they're not soluble. How about methanol, CH3OH, it's an alcohol, and KBr, potassium bromide. Are they polar or nonpolar? Let's see. CH3OH, polar or nonpolar? It's polar. KBr, potassium bromide, polar or not polar? It's a bit of a trick question here. Potassium bromide is ionic. Ionic. So I guess that's the third thing. Is it polar, nonpolar, or ionic? So polar and ionic compounds, are they soluble? Can they engage in intermolecular attractions? They can. They can form dipole ion attractions, so it's like water and salt. Okay? So these two are soluble. And the attractive force that holds them together is a dipole ion attraction, or ion-dipole. Sorry. Ion-dipole. And lastly, are these two polar or nonpolar? CH3OCH3, polar or nonpolar? Has an electronegative oxygen, so it's polar. CH3OH, we already said in problem B that it's polar. Okay, so we have two polar molecules. So are they soluble? Yes. They're both alike because they're both polar. If soluble, identify the attractive forces involved in their interaction. So London forces check, but they're polar, so they're also going to have dipole-dipole attractions. Check. Do they have hydrogen bonds is the last thing to check for. This one has an oxygen by itself that's not bound to hydrogen, so it has a hydrogen bond acceptor. And this one has an oxygen that's bound to a hydrogen, so it has a hydrogen bond acceptor and a hydrogen bond donor. Okay, so there's a hydrogen bond donor on this one, hydrogen bond acceptor on this one, so yes, they can engage in hydrogen bonding. So I'm going to say that they have both, well, I'm just going to say the strongest force. That's involved in their attraction, which is H bonding, hydrogen bonding. But technically, they have hydrogen bonding and dipole-dipole bonding and London forces. But this is the one that's the strongest, okay? So that is how intermolecular forces affect solubility, okay? Intermolecular forces affect the ability of molecules to dissolve one another. If two molecules, if you have polar molecules that have very strong intermolecular forces and you throw in some nonpolar molecules, they're not going to be able to mix because they can't engage in that same level of attraction. It's basically the simple, you know, the answer, how I make them into like people and relationships. Okay, so another thing intermolecular forces influence are changes of state, so changing from solid to liquid to gas. So what happens when you heat a substance? When you change it from solid, liquid to gas, usually you're heating it. So like water being the example, you have ice, you heat it, and what happens to the molecules? They start moving faster. And when molecules, by definition, are moving faster, they become more liquid. It's because when they move faster, it starts breaking those intermolecular forces. So you have these intermolecular forces. It's just hand-holding, okay? But if you start shaking those molecules around, it's going to be too much energy. They're not going to be able to hold hands anymore. They're going to break apart. And then that's going to lead to the changes of state, okay? So you have solids, liquids, and gases. And remember, the molecules all kind of move. I don't know if this slide is animated. Let's see. I can't remember if I had the molecules moving around. I guess I did not. Okay, had to check though. So when you go from a solid to a liquid to a gas, when you change from one state to another, there's vocabulary words, okay? So these are called phase transitions. Moving from one state to another is called a phase transition. So moving from solid to liquid, as we all know, is melting. So you have ice, turns to water, it's melted. When water boils and becomes gas, we call that vaporization. So when a liquid becomes a gas, it's called vaporization. When a gas becomes a liquid, it's called condensation. Think about, again, a glass of ice-cold lemonade on a hot summer day. Water vapor in the air from humidity condenses onto the glass, turns into liquid. All right, and then when liquid turns to solid, it's called freezing. So how does this all happen? Why do we have solids, liquids, and gases? Essentially, it all has to do with intermolecular forces. It's the intermolecular forces, the London forces, the dipole-dipole attractions, and the hydrogen bonds that keep the molecules together and hold them together either in a solid, liquid, or gas state. And the colder the molecule is, the slower the molecules are moving, the more likelihood that they can form those intermolecular forces and keep them there, okay? So let's say you have a bunch of kids in a room and you tell them all to hold hands. They can all hold hands, okay? And now tell them to stand still and hold hands. Then they can do that. That's a solid mass, all right? You tell them to keep holding hands and start running around. Well, their hands are going to start breaking apart. They're going to start breaking some of those intermolecular forces because they're moving at higher speeds and there's more energy. You tell them to bomb around the room as fast as they can, well then none of them are going to be able to hold hands anymore. They're all going to separate and they're going to be these gas molecules. So in a gas, essentially, there's no intermolecular forces because the particles are moving too fast and they're too spread out. So essentially, in gas, you don't have intermolecular forces. They hold together the molecules in liquids and solids, but when you heat molecules and they move, they have so much energy, they actually overcome those intermolecular forces, then you get a gas. So what is the boiling point of something? The boiling point is the temperature at which molecules in a substance go from a liquid to a gas, okay? And in order for molecules to do this, two things sort of have to happen. One, there has to be enough energy in the system for the molecules to overcome the attractive forces between them, okay? So their hands, the intermolecular forces have to be broken. Secondly, molecules have to overcome atmospheric pressure. So it's not just enough for the bonds between them to be broken, they also have to have enough energy to overcome the pressure that's pushing down on them from the atmosphere. So my analogy here is to a game of capture the flag. So if you, it's been a long time since I played capture the flag, but if I remember it correctly, there's like a line and there's two teams and there's a flag and you try to run to the line, the other team's side and capture their flag and bring it back to your side. If you cross over the line and you get tagged by someone on the other team, then you go to jail, in their jail, okay? And if lots of people on your team get put in jail, you all have to stand in line and hold hands in jail, and someone from your team can come rescue you by tapping the person in jail, and then they can get out. So there's sort of two things that have to happen if you're stuck in jail for you to get out of jail. One, someone has to tag you and allow you to break that bond so you let go of the people in jail. But then you also have to get out of the other team's zone and get back to your team safely without getting tagged again. So there's two things. You have to get tagged, so you have to break the chain gang, and two, you have to get safely to the other side. So same thing, molecules, like in a liquid, they have to break the intermolecular forces and they have to break out against the pressure of the air pushing down. So that is how boiling occurs. So a boiling point of a compound of any substance is actually going to be very dependent on, it's dependent on atmospheric pressure, but aside from that, it's going to depend on how strong the intermolecular forces are. The stronger the intermolecular forces, the more energy you need to disrupt them. Okay, so take these two alkanes, for example. Pentane, C5H12, has a boiling point of 36 degrees Celsius, and octane, which is C8H18, has a boiling point of 125 degrees Celsius. They're very similar molecules. They're both nonpolar compounds that only have London forces holding them together. So why is the boiling point for octane so much higher than the boiling point for pentane? Okay? It has to do with the type of intermolecular forces. So remember, what did we say in the beginning about London forces? They're weak, but they get stronger as the molecule gets larger. So pentane is fairly small, octane is larger. There's more atoms in the molecule to engage in London forces. So the bigger the molecule is, the stronger the London forces. So this one has stronger London forces. Therefore, it's going to have a higher boiling point because there's more London forces to sort of disrupt in order to get the molecule into the gas phase. So that's why compounds that are similar can boil at different temperatures, because the forces between them can be very different. So here's a chart of different alkanes, okay, small one, the smallest one, methane, up to decane. So this is similar to the chart that was in Chapter 4, I think, going over the different fatty acids, or Chapter 4 talking about the different alkanes, the first 10 alkanes, okay? But now we're showing their boiling points. So the smaller ones have very low boiling points. In fact, methane's boiling point is negative 161 degrees Celsius. Room temperature is about 25 degrees Celsius. So room temperature is much higher than the boiling point of methane, which is why methane is a gas at room temperature. In fact, these first 4 on the list here are all gases at room temperature because they boil at very low temperatures. They turn to gas because they have very few intermolecular forces holding them together. So they have to be pretty cold in order to form these intermolecular forces to keep them in a liquid or even to try to get them to a solid state. I'm not even sure there is such a thing as solid methane, how cold you would have to make it. So as the carbon chains get longer, though, as the molecules get larger, their London forces get stronger because they're bigger, and they have higher and higher boiling points. So all of these, pentane through decane, are all liquids at room temperature, because at room temperature, 25 degrees, that is below their boiling point. So they exist as liquids. So here's another question, another sort of application of boiling point and alkanes. Here's two molecules that have the same molecular formula. They're two isomers of hexane, okay? So C6H14. This is C6H14. And this is also C6H14. It's a different isomer called 2,3-dimethylbutane. 2,3-dimethylbutane, because there's the longest chain here is 4, butane, and it has 2 methyl groups coming off carbon 2 and carbon 3. Okay, so hexane and 2,3-dimethylbutane are isomers of each other, structural isomers, and they have different boiling points. Hexane has a higher boiling point than dimethylbutane does. Why the hell do you think that is? You'd think that they would have the same London forces because they're the same size. They both are, let's first point out, they're both nonpolar. So the only attractive forces between them are London forces. And you would think they're the same size, they have the same number of carbons and hydrogens, so they must have the same strength of London forces. But they don't, okay? The rule here is that straight chain alkanes always have a higher boiling point than branch chain alkanes. And why do you think that is? I don't have a slide on it, but essentially, think of it this way, okay? Take these hexane molecule here and draw another one in your head. Draw a whole bunch of these hexane molecules. Let's see, wait, hold on, let me see if I can do this in here. No, I can't. Let's do it here. Okay. Let's do it. No, I can't. Ugh. All right, I'll draw it. Okay. So we have a whole bunch of these hexane molecules. 1, 2, 3, 4, 5, 6. All right, notice how they all stack very nicely. Okay? In other words, I like to say these molecules can spoon really well. You know, like when you're laying in bed with your spouse and you like hug each other and you snuggle like spoons in a drawer. A bunch of spoons fit together very nicely, okay? Straight chain alkanes can spoon really well. However, branch chain alkanes cannot spoon very well. They're spiky and branched and they stick out in different directions and they don't pack as nicely together. So you can't get as much London forces between them because they don't spoon well. In order to have London attractions, the molecules have to be able to get close enough to each other to attract each other. And these guys are just too spiky. 1, 2, 3, 4. 1, 2. All right. Try spooning with one of these guys. All right. That's why the boiling point for straight chain alkanes are higher than for branch chain alkanes because they spoon better, okay? And so therefore they have more London forces. So water is a little bit weird, okay? It's smaller than pentane. And remember, pentane's boiling point was 36 degrees, but it has a higher boiling point. So why is that? It's smaller. I thought we said that as molecules get bigger, the boiling point gets higher, right? But it's not about the size always. It's about the attractive forces, okay? So water has a very high boiling point because it has hydrogen bonding. It has the strongest type of interactions of intermolecular forces. So you need very high energy to be able to break those attractive forces. So the stronger the attractive force, the more energy that's needed to overcome it, thus the higher boiling point and the higher melting point for that matter. So if you compare two things, one nonpolar molecule to a polar molecule, the polar molecule is probably going to have the higher boiling point. And that's what we're going to do in this sample problem here. For each of the following pairs of compounds, predict which substance would have the higher boiling point, just based on the structure. Okay? You don't have to know what the exact boiling point is to know which one's going to have a higher boiling point. So, CH3OH versus CH3CH3. So, methanol versus ethane. Which one do you think has a higher boiling point? This is the correct answer, methanol. Hopefully you got that too. Why is that? Because this compound, ethane's boiling point is based on the fact that ethane molecules are nonpolar and are held together by London forces, which are not very strong. Whereas methanol here, similar size molecule, okay, has London forces, but it also has an OH group, and this OH can engage in hydrogen bonding. It's a hydrogen bond acceptor and a hydrogen bond donor in one. So hydrogen bonds are stronger than London forces, therefore this one's going to have a higher boiling point. How about these two molecules? Which one is going to have a higher boiling point? This one is 1, 2, 3, 4. Butane. Butane versus 2-methyl-propane is what this one would be called. It's got a chain of 3, propane, and it's got a methyl group coming off the second carbon. So 2-methyl-propane versus butane. Butane's going to have a higher boiling point. Why? Because straight chain alkanes have a higher boiling point than the branch chain ones. Now compare these two. CH3NH-CH3 and CH3OH. Which one's going to have a higher boiling point? Ooh, this is a toughie. So I'm going to draw this one out so we can see it better. CH3N, and that H is attached to the nitrogen here, and CH3. Alright, so what's the strongest type of London force, of attractive force, that this molecule can have with itself, like with other molecules like this? It can engage in hydrogen bonding. It's got a nitrogen with a hydrogen attached to it. This is a hydrogen bond donor and a hydrogen bond acceptor. Here's the lone pair on the nitrogen, okay? So we can do hydrogen bonding here. H bonding. So this one might be the winner because hydrogen bonding's pretty strong, so that's probably going to be the higher boiling point. But wait a second, this one here also, it has an OH group. It has a hydrogen bond, ability to hydrogen bond as well. Hydrogen bond acceptor in the oxygen, hydrogen bond donor with this hydrogen. So this one also can engage in hydrogen bonding. So which one is going to have a higher boiling point? How might you figure that out? Okay. Well, I'm pretty sure I know the answer, but I just want to double check here. Okay, so both of them, I'm reading the answer out of the textbook to make sure I'm explaining this correctly. Both of them have dipole-dipole bonds. Both of them have hydrogen bonding attractions, okay? And they both have can engage in the same amount. So both of them have one hydrogen bond acceptor and one hydrogen bond donor. So it's not like one can engage in 5 hydrogen bonds and the other can only engage in 2. Okay. Oh, nope, that's wrong. Okay, so let's draw this one out, the methanol. Ooh, this was a good one. Stumped me temporarily. Okay. So, it looks like this. And we have our 2 lone pairs here. So each of these lone pairs can be a hydrogen bond acceptor. Okay, so technically we have 2 hydrogen bond acceptors here and 1 hydrogen bond donor with this hydrogen. In this molecule, nitrogen only has 1 lone pair, so it's a hydrogen bond acceptor. We have 1 hydrogen bond acceptor and 1 hydrogen bond donor. So technically, this molecule, the methanol molecules, a whole bunch of methanol molecules together, can engage in sort of 3 hydrogen bonds with each other. So you can have 2 hydrogens bonded to this oxygen, and you can have this hydrogen bonded to one other oxygen. So basically it can have 3 attachments, 3 hydrogen bonds, whereas this molecule can only have 2 hydrogen bonds with other molecules. So the winner here, the higher melting point, or higher boiling point, either one, would actually be the methanol, because it can actually engage in slightly more hydrogen bonding than this one. So that's a pretty tricky one. I don't think I would ask something like that on the test. But it's good to challenge yourself, right? There you go. Okay, so in this chapter we come back to talk about lipids again. It's a little bit redundant or maybe it's just redundant because I already covered some of this stuff when we did talk about fats originally in chapter 4, but fats are pretty important molecules, so it's okay, we're going to talk about it again. So we did talk about saturated fats, unsaturated fats, trans fats, and we talked about saturated fats or animal fats being solid or semi-solid at room temperature, and how oils are liquid at room temperature, unsaturated fats, and both of them are made of triglycerides. So why are they different? In different physical states, one is solid at room temp, one is liquid at room temp. Why is that if they are both made up of triglycerides? And if you remember, I showed you a picture like this saying that the saturated fats have these long straight chains of single bonds, and that they pack more densely together, kind of like your textbook. The pages pack very tightly together when they're straight, but if you drop the textbook in the toilet and the pages got all wrinkled and ruffled, okay, then it wouldn't close as tightly. That's what happens with unsaturated fats, because the double bonds cause them to have kinks in the chain and they don't pack as tightly together. Well, what I mean when I'm talking about packing tightly together, I'm meaning how well the molecules spoon and how many London forces, how strong the London forces are. The straighter they are, the more, it's just like straight chain alkanes versus branch chain alkanes. Straight chains spoon better and therefore engage in stronger London forces, and stronger London forces mean that they can be more solid, okay? Whereas when they're kinked and they're all bent out of shape, they can't pack as tightly, they can't spoon as tightly, okay, so I guess they're more like this, and therefore they have fewer London forces, attractions, holding them together, so they become more liquidy. They have a lower boiling point, okay? But as we all know, M&Ms, what is it? They melt in your mouth, not in your hand. Except that's not really true. They will melt in your hand, okay? That fats melt in your hand. They melt at low temperatures because even though saturated fats like butter, for example, even though butter is solid, more or less at room temperature, you put it in your hand, you expose it just to a little bit of heat, it melts very quickly, because even though you have a lot of London forces holding it together and making it somewhat solid, London forces are still pretty weak and pretty easy to break. So they still have a very low melting point because London forces are still weak forces. Okay? So we talked a little bit about unsaturated fats, saturated fats, and trans fats. And I mentioned, I'm talking about this. I think I even showed you a picture of the difference between a saturated fat, or sorry, an unsaturated fat that has a kinked chain versus a trans fat that has a double bond but is still sort of straight chained, okay? So the way that we actually, but I didn't talk about how trans fats are made, how they're made to be trans as opposed to cis. Okay? And it's a process called hydrogenation. So they take, in the industry, they can take unsaturated fats, so oils with a bunch of unsaturated fats, a bunch of cis double bonds, okay? And they hydrogenate it. So they basically forcibly add hydrogen to that double bond, so now it's a single bond. So they take unsaturated fat and they convert it into a saturated fat by hydrogenating it. Okay? And but if they did that, then that'd be kind of pointless. There's plenty of sources of saturated fat. The point was to try to make foods that were partially hydrogenated. So some of the double bonds were broken, but you still wanted them to have double bonds because then they were still unsaturated and they thought that was healthier. So margarine is partially hydrogenated, or originally margarine was made as partially hydrogenated oil. So it's less saturated than butter, thinking that that was healthier, but it's more saturated than oil, which is what makes it solid. So that's why it had these, they designed margarine to have these desired properties, which was they wanted it to be less saturated than butter, because saturated fat was thought to be very bad for your heart health. But they wanted it to be more saturated than oil because they wanted it to be solid. And the problem, or the thing is that when you incompletely hydrogenate something, you partially hydrogenate something, it turns those double bonds in the cis configuration into a trans configuration, which is why we get trans fats. So you take this oil here, this is a triglyceride that contains 3 different unsaturated fatty acids, because they all have double bonds in them, and you add hydrogen, okay, and it partially hydrogenates, so a lot of those double bonds get converted to single bonds, but one of those double bonds ends up flipping back into, or I guess one of those single bonds ends up flipping back into a double bond, so you don't get quite total saturation here. But now instead of having a cis double bond, you have a trans double bond, so now we have a trans fat, okay? And notice, this picture doesn't show it very well, but these cis double bonds, remember, are the ones that are kinked and are kinky, so they don't pack as well. And so this is going to be an oil, it's going to be liquid at room temperature. But this trans fat here looks much more saturated, and the chains are straighter. And so this fat will be much more likely be solid at room temperature. Okay? So that is a little bit more detail about unsaturated, saturated fats, and trans fats, and which ones and why they have the physical properties that they do, why they are solid or liquid at room temperature. So the last part of the chapter talks about intermolecular forces and the cell membrane. This is the part that's really relating it back to biochemistry and biology and physiology. Our bodies are made up of cells, and cells contain membranes. Cells contain solutions of things. Things need to be soluble in your blood and in your cells, and so that's sort of where this intermolecular forces is coming in. And intermolecular forces are also how your cells are sort of held together, okay? So the cell membrane of a cell is made up of these types of lipid molecules called phospholipids, which are amphipathic molecules. They have a head group here. So it's looks kind of like a triglyceride. You have a glycerol backbone and 2 fatty acids. So a triglyceride is a glycerol molecule with 3 fatty acids. But a phospholipid has only 2 fatty acids, and then at the 3rd site on the glycerol, it has this phosphate group, okay, containing a phosphorus molecule, a phosphate group. And the phosphate group is usually charged. Notice this one has a negative charge and a positive charge in it. And that makes it very polar, very hydrophilic. It likes water. It likes polar molecules. Whereas the fatty acid tails are very nonpolar. So again, we have ourselves an amphipathic molecule. What else did I talk about in this lecture that was an amphipathic molecule? Soap. Remember, soap was an amphipathic molecule. A hydrophilic head and a hydrophobic tail. Okay, so soap and phospholipids look very similar to one another, except that if you kind of like look at the geometry, they're a little bit different shapes. So soap molecules kind of are a little bit more triangular in shape in terms of their head to their tail, whereas because phospholipids have 2 tail groups, it makes them more sort of rectangular in shape, which means that the structures that they form are different. So my cells, because they're triangular in shape, soap molecules form my cells because they're kind of triangular in shape, and you put a bunch of these triangles together, and it starts curving, and it ultimately forms this nice sphere. Now, phospholipids can actually form spheres as well, but they're larger and less likely to happen. The structure that phospholipids really like to form is this one right here, called a phospholipid bilayer, because they're more sort of rectangular in their shape. And this is what our cell membranes are made up of. They're made up of these phospholipid bilayers. Layers of phospholipids, so their hydrophilic head groups, are on the outside and inside of the cell, because outside and inside of the cell is a very aqueous, watery environment. Your body is like 70% water. Remember that video I made you watch briefly about carbon, and they said if you pull all the carbon out of your body or whatever, it's like 70% water, and it was a little cartoon character that's 70% full of water, okay? You have a lot of water in your body. And there's water inside your cells, there's water outside your cells. So the phospholipid bilayer is set up that all of the head groups, the hydrophilic head groups, outline the cell, and then the hydrophobic tail groups face each other and interact with each other that way. So this phospholipid bilayer also is very important in regulating things that can go inside and outside of the cell. If the whole thing was polar, then polar molecules could very easily go in and out of this phospholipid bilayer. But because it has this nonpolar region in here, it becomes very selective about what can go in and out of the cell. So the cell membrane is not just made up of phospholipids. So you have the phospholipids, and that's the tan molecules in here. But there's also a whole bunch of other crap that's shoved into the membrane that gives it a lot of different properties. So again, because large polar molecules can't go through this membrane because there's this nonpolar region in the middle, there has to be proteins, channels, that allow things to go in and out of the phospholipid bilayer. So there's also cholesterol that's embedded in the phospholipid bilayer. That's these little yellow molecules here, cholesterol. And that actually affects the fluidity of it. So it's the more cholesterol that's in the membrane, the more flexible that membrane's going to be. There's these carbohydrate side chains here. So so we talked about in the last lecture, in Chapter 5, about oligosaccharides that act as cellular name tags. So that's what we're talking about here, like the ABO blood groups, these little branched carbohydrates, these little oligosaccharides sticking off the cell, act as cellular name tags. So if this was a red blood cell, this could be an ABO, an A or B antigen sticking off here. Also, it could be an antigen that says, I'm a liver cell, I'm a kidney cell. There's all different types of carbohydrate sort of tags, oligosaccharide tags. So this whole thing, this whole membrane, is actually held together by intermolecular forces. London forces on the inside here, and dipole-dipole forces on the polar sides of the molecules. So these intermolecular forces, because they're strong, they're relatively strong, they actually keep all these molecules together to form a membrane. But you wouldn't want your cell membranes to be all covalently bonded together. You don't want them to be super glued together because they'd be too stiff, right? Okay, so these proteins and things, they can drift about through the phospholipid bilayer. They can move around on the outer surface of a cell. So if you have a protein that's here on your cell membrane, it can actually move to other sides of the cell if it needs to, if it wants to. It's called a fluid mosaic model of the cell membrane. So a mosaic is when you have a lot of different pieces of different things that are sort of, scattered together, and fluid meaning that it's flexible, it can move. And so the fact that we have these intermolecular forces actually allow for this miraculous fluid mosaic model of the cell membrane, allows proteins and things to sort of float through the membrane, and they're not physically, permanently embedded in those places. It allows us to do things like, for example, when you regulate your blood sugar, there's a transporter, a protein in the membrane that's called the glucose transporter that allows glucose in and out of the cell. If your cell needs a lot of glucose, like maybe a muscle cell because you're exercising, the cell will actually send more glucose transporters up to the membrane so that more glucose can get in. And then when your cell doesn't need that much glucose anymore, it pulls those glucose transporters out. So it gives the cell a lot of flexibility to decide what can come in and out of the cell, because these things are all sort of held together by intermolecular forces, which are strong enough to keep them together, but weak enough that they can be broken if needed. So intermolecular forces, what that means is that intermolecular forces, they're pretty cool. It's how we are held together as people. It's how our cells are held together through these intermolecular forces. It's how the table that my computer sits on is held together. If there were no intermolecular forces and I put my hand down on this table, it goes straight through. Okay? It's not that all the wood molecules are covalently bonded together. The world is not about covalent and ionic bonds, which are pretty important for molecules, but the world is held together by intermolecular forces. Everything around you that you see are molecules that are held together by intermolecular forces. I just think it's pretty cool. If you didn't have them, the world would fall apart. Or alternatively, if you only had covalent and ionic bonding, there'd be like no flexibility in anything. You wouldn't be able to break things apart because you can only do that because they're somewhat weakly held together by intermolecular forces. So, like, you couldn't cut a piece of paper if it was all covalently bonded together. You couldn't cut it with scissors. You'd have to chemically break it apart. There would be no such thing as physical changes, as going from solid to liquid to gas. That wouldn't happen if there were no intermolecular forces. So it's pretty cool if you think about it that way. Maybe it's just cool for me because I'm a big geek, but I think intermolecular forces are pretty cool. In fact, my chemistry, I think my college chemistry professor, the last day of our lecture, we talked about intermolecular forces, and that's what she said. She said, my hand would go straight through this table if there were no intermolecular forces. And I thought, wow, that's really cool. So intermolecular forces determine pretty much a lot of physical properties, determines whether things are soluble, determines whether something is solid, liquid, or gas. And it determines the flexibility of your cells and what is allowed in and out of cells. So it has a lot of implications. In the next chapter, we're going to talk about solutions. So we're going to apply some of this stuff that we know about whether things are soluble, and then we're going to talk about the different types of solutions. And solution chemistry is physiology. I mean, your body is just a bunch of solutions. Your blood, your spit, all the fluids inside your cell and outside your cells are all solutions. And everything you put in your body is a solution. When you drink a Gatorade, all right, when you inject a drug, all right, they're all solutions. And understanding solubility is a big part of coming up with drugs and coming up and understanding how nutrients are digested and absorbed and metabolized, which we'll get to later. So the foundations in this chapter we're going to see again in all of sort of the upcoming chapters. So understanding intermolecular forces is something that's going to be carried out throughout the rest of the book. So make sure that you're sort of clear on these different forces, London forces, dipole-dipole attractions, and hydrogen bonding, because we're going to keep talking about them. So work the problems and contact me if you have any trouble, any questions. I'm happy to go over them, maybe do some more problems. I can post another video, or we can talk it out over the phone or Skype. So that's all. Thanks for watching. Bye now.